Okay, now we'll talk about eigenvalues and eigenvectors, and these are what I was referring to in that video on Leslie matrices, but we're not confined to just considering Leslie matrices. We could use any square matrix A, and then we could set up this equation where V is just a vector of unknown quantities, and this Greek letter alpha, lambda is just an unknown constant. Okay, and as we saw in that Leslie matrix example, that vector V gives the stable proportions of the different life stages present in the population in the long run. Okay, and this lambda gives the growth rate of that population. Okay, but that's just one interpretation of this equation, and as we'll see throughout the rest of the course, this pops up in many different contexts and has many different useful interpretations. Okay, but let's look at the mechanics first. So I've got a very simple 2x2 matrix here. I can set up this vector of unknowns and set up this equation like this. Okay. And you can see if I do this matrix multiplication, I'm going to get a system of equations. So let me do that here. I've got 1v1 plus 3v2, and that's equal to lambda times v1. And that second multiplication is 2v2, which is equal to lambda times v2. Oh, and you look, I've worked out what lambda is. Lambda is equal to 2. And this is the eigenvalue corresponding to this equation here, this matrix. And then I can sub it in, for example, into this first one. And then what I'm left with is v1 plus 3v2 is equal to 2v1. Now, if I solve that, I get 3v2 is equal to v1. And that's as far as I can take that. So what this has shown me isn't explicit values for v1 and v2, but rather how v1 and v2 relate. Okay, so I can put in any values for v2 and v1. Oops, there's my eraser. I can put in any values for v1 and v2, so long as they satisfy this relationship here. So for example, I may as well put 1 here, and then I would get 3 for that. Okay, I should say any non-zero value, right? Because I could have just put 0 equals 0. That's not too interesting. Erase that, and let me put that eigenvalue here. Okay, and get rid of these guys, and put those values for the eigenvector in there. Okay, and now I can see if this actually works out. Okay, so I'm going to do that, this multiplication on the right. First, I've got 3 plus 3, so that gives me 6. And then down here I've got 2. Sure enough, that is equal to the right-hand side. Okay. This multiplication, for those of you following along at home, this multiplication gives me this vector, which is 2 times that original vector. So this is what an eigenvalue and an eigenvector pair look like, that multiplying by the matrix, multiplying this eigenvector by that matrix, is the same thing as just multiplying that vector by the eigenvalue. Okay, so it's just a scaling. That matrix acts like a scaling of this vector in this case. Okay, so we could try it again down here. I could set this up, v1, v2, and that's going to be equal to some unknown lambda, like that. And we do the same thing. Got v1 plus 2v2 is equal to lambda v1. Then I've got 3v1 plus v2 is equal to lambda v2. Okay, and now I could try to solve this in some way. What's a good way we could do it? Well, maybe we'll just rearrange it like this. I've got 1 minus lambda v1 equals minus 2 v2. And then down here, I could do something similar. I've got well, lambda minus 1 v2 is equal to 3 v1. Yeah, now we've got, you know, a bit of a problem perhaps. It's not too clear what we should have. It looks like lambda should be 3. Well, no, we can't really determine it, right? It's not like this first case where we had this very simple calculation and then lambda just came out in the end as 2. Here it's kind of difficult to think about, let alone solve. So it would be nice if we could come up with a nice rigorous way of finding these every time. In order to do that, we're going to take a little closer look at this, which we'll do right now. So here's that equation. I could subtract this from both sides. I get this. And now I want to take out that vector v. So if I do take out that vector v, I need to multiply it by something that will make sense, that will reverse that operation. So when I distribute this vector in, I should end up with this over here. Now, in order for that to happen, I have to introduce the identity matrix, the appropriately sized identity matrix here. Okay? Because, think about it, I've got a vector here, I've got a scalar here, so I need some sort of matrix here in order for that multiplication to be defined. Okay? So now, this equation is true when either part of that product is 0. Okay? In this case, that means that this is not invertible. Okay? And that's something that we can revisit in a little bit. And what that means, if you think back to the videos on invertibility, remember what it means to have an inverse, that we can multiply both sides of an equation with that. It's kind of like the division, the analog of division. But you remember when a matrix is not invertible? One case is when we have a matrix where the rows are not linearly independent. Something like that, for example. Okay? We can check if they're linearly independent because we row reduce them, and we would end up with a row of zeros here, which causes all sorts of problems. Okay? In particular, we can do something called finding the determinant of this matrix. And then we can see the value of that determinant, and it will tell us if the matrix is invertible or not. Okay? And watch how we do it. You notice here that if I multiplied these and then multiplied these together and added them or subtracted them, that I would end up with 0. Okay? That's the heart of this determinant calculation. Let me show you what it looks like. Just get rid of the simplified matrix and work here. So with a determinant calculation, the way I do it is I multiply those two 2's together, and then I subtract this 1 and this 4. Okay. This is the determinant of a 2 by 2 matrix. It's this times this minus this times this. And you notice it gives me 0. Okay. Let's look in other contexts here with other matrices, and we'll calculate the determinant. Here the determinant is just 1 times 2, and then minus 3 times 0. That's an easy one. That just gives me 2. And you might remember that this is the matrix we found the eigenvalue and the eigenvector for in the previous slide. So this is not invertible because the determinant is not 0. You notice here there's a pattern emerging that the rows are linearly dependent, and when I take the determinant I get 0. Here the rows are not linearly dependent, they're independent, and when I take this determinant I get something that's non-zero. Okay, now let's try here. These are linearly independent. You could just do that by inspection. You can see 2 times 2 is going to give me 4, but 2 times 1 will just give me 2 and not 3. So I expect here to get a non-zero determinant, and let's try. I have 1 times 4 minus 2 times 3. Sure enough, it's not 0. I've got 4 minus 6, so minus 2. Now let's try this here. I should just say, these are just various results that we could get when we're finding the determinant. Okay, and there is that connection, which we're going to keep on talking about and really explore, that when we have rows that are linearly dependent, we get a 0 for the determinant, and when they're linearly independent, we get non-zero entries. Okay, so I want to find the eigenvalue of this matrix. The way I'm going to do it is set up this equation, and I'm going to solve it. Okay, and the way we do it is I take this A, this is my A, and I'm going to subtract lambda times the appropriately sized identity matrix, like this. Okay, and then I'm going to take the determinant of this whole thing. Now you can write the determinant as these kind of vertical bars like I've been writing so far, or you could also write DET for determinant. Either's good. Okay, so first what I'm going to do is actually this matrix subtraction. Remember that when we have constants, they multiply all the entries of the matrix, so this is just going to be lambda 0, 0, lambda. And when I do that subtraction, I get 1 minus lambda, or 1 minus lambda in this entry, then 2, then 3, and then 1 minus lambda down here. Okay. Now the determinant is these two multiplied together. So 1 minus lambda times 1 minus lambda, so I'll just write it like this, squared, minus 2 times 3. Okay. I can work that out a bit. I'm going to get lambda squared minus 2 lambda plus 1 minus 6, so minus 5. Just double check that in my mind. And that looks good. So now we could find the lambda that satisfy this. And sure enough, these are going to end up being those eigenvalues. Okay, so we could use the quadratic formula here if we so choose. I'm trying to do it in my mind. I don't think I'm quick enough. So let's go negative b plus or minus the square root of b squared. So 4 minus 4 times a times c. So minus, minus 4 times a times c is plus 20. This is why I couldn't do it in my mind. It looks like it's fairly complicated. So then I would have 1 plus or minus square root of 24. I'll just write it like this. 24 over 2. The square root of 24 over 2. And you could simplify it that if you want. But these are the eigenvalues for this matrix. Okay? And like I said, we're going to get some practice with doing this mechanically, and then we'll go on to interpretations, because they tend to be very important. Okay? And what I have here is just some practice for you to do, and we'll talk further about this in the upcoming videos.